Okay, everybody, I'm going to walk you through the review for test number 2. So, again, this is a non-edited video, so you get what you get. If I find a mistake, I'll correct it. If I don't, you're going to let me know, right? So, use this practice test review at your own risk. Okay? Anyway, here we go. First thing I'm going to look at is a counting problem here. All right, so let me scroll down. I got to get my pen working here, and got to make sure everything, yep, here we go. We got things going here, I think. All right, yeah, there we go. All right. At a Sundae shop, there are 7 different flavors of ice cream and 6 different toppings. How many sundaes can be made if 3 different flavors and 2 different toppings are chosen? So, remember, the counting routine says the first thing we have to do is say what we got to do. We need 3 different flavors, right? So we need the first flavor, the second flavor, the third flavor. Then we need 2 different toppings. So we need a topping and then another topping. So that's step 1. Step 2 is where are they coming from? Well, our flavors are coming from 7 different flavors. Our toppings are coming from 6 different toppings, right? Step 3, you start selecting. So when I pick the first flavor, I have 7 choices. But the question now is, can I pick the same flavor? Well, it says 3 different flavors. So I can't put something back. My number's going to start going down. So 6 choices for the second flavor, 5 choices for the third. Now I get to toppings. It's all multiplication, remember? Okay, so I'm putting my little multiplication sign there. You know it don't look like one. Okay, I gotta get used to this. All right, anyway, when I get to the toppings, I have 6 choices for the first one. But once again, I need to use 2 different toppings. So when I get to the second topping, there's only 5 left. So that was step 3. Step 4, do I have order? That is, when I select a particular flavor, does it matter at which time I select it? I'd say in the context of this problem, no. There's no order. And for the second one, the context, once again, is there's no order here. Okay? I would think somebody's strange if they said I have picking strawberry first over chocolate is different. All right? Anyway, so since I don't have order, I am going to have to divide. So let me just get rid of this right here. When you don't have order, you divide. Well, how many flavors did I pick? I picked 3. So I divide by 3, 2, 1. How many toppings did I pick? 2. So 2, 1, right? So when you don't have order, you're going to be dividing. You divide by how many you selected, factorial. I selected 3 flavors, 3, 2, 1, factorial. I selected 2 different toppings, 2 factorial, 2 times 1. Remember, it's all multiplication and or division. So you can multiply the top numbers together, and if I'm correct, you're going to get 6,300. You multiply the bottom numbers together, 6 times 2 is 12. If you do your math, you will get 525. Oh, 525. So that's the first one. Okay? Moving on to the second problem. How many IDs can be made up of 3 letters if repetition is not permitted? 3 letters, repetition is not permitted. Step 1, I need 3 letters. Where are they coming from? Well, 26 different letters. We don't distinguish between upper and lower case. If we did, we would indicate that, all right? So there are 26 different letters. I start to select, step 3. When I start picking, can I put something back? Repetition is not permitted. So in other words, the letters have to be different. So my number is going to be going down, 25, 24. Do the math, you get 15,600, right? Now, what did I forget? I forgot to say, is there order? That is, does it matter if A comes before B? And it does, because it's an ID. Think of a name, okay? Pat, P-A-T, is different than Tap, T-A-P, right? All right, if your name's Pat, you wouldn't want somebody to call you Tap, right? So there's order when you have IDs, passwords, license plates, names, etc. That's number 2. Moving on to the next one, we have a committee. It's to be made up of 3 people. It's selected from a group of 11. And the question is, how many possible committees are there? So we're going to go over here and do our work. I'm going to erase this stuff up here so I have room, okay? You have it now. You can always rewind the video, right? Okay? That's what you can do. All right. For number 3, I need to pick 3 people to be on the committee. Committee member, committee member, committee member. They're coming from 11 people. I start to select 11 choices for the first. I can't put them back because I need 3 people on the committee, so my number's going down. The next question is, question 4, is, well, is there order here? Well, if you pick first, you're on the committee. If you pick second, you're on the committee. It makes no difference, right? So notice this is different than number 2 because there is order in the context of the concept of an ID, right? But for number 3, if you're first, you're on the committee. If you're second, you're on the committee. So once again, we don't have any order. So that tells me I need to divide this product by, how many did I pick? 3. So 3 factorial, 3, 2, 1, right? If you do your math, you should come up with 165. So that's 3A, 165. The second part of 3 changes the problem a little bit. The committee is going to have a president and a secretary. So now this is what's going to happen. If I erase this, because again you can rewind the video, that's the beauty of the video, right? It's a beautiful video. But anyway, when I pick the committee now, I need to pick a president, I need a secretary, and then I need somebody else on the committee because I need 3 people, right? So once again, they're coming from 11 people. I have 11 choices for the president, but I can't put them back. So once again, my number's going down. We want to browse in private with Avast Secure Line? I don't think so. Whatever that means. So let me close that. So 11, 10, 9. All right, so now that I did step 3, step 4, is there order? Well, yes, there's order here because if you're selected first, you're president. Second, you're secretary, and third, you're just on the committee. There's order here, and when there is order, you're done. You don't have to divide by anything. So, 11, 10 times 9, and the product of that is 990. So for the second part, it's 990 because we have order here. Okay? Now notice how this number is larger than the first one because again, when you don't have order, you don't care about certain arrangements that are part of that 990, right? Moving on to number 4. How many IDs can be made up of 5 letters if repetition is not permitted and the first letter has to be R? So this is a little bit different, this problem. How many IDs can be made up if we have to have 5 letters, so we need a letter, a second letter, a third letter, a fourth letter, and a fifth letter. Now the first letter has to be R. So you know what? This one has to be R. So we now listed what we have to do. Where are they coming from? Well, we have 26 letters, right? But now, when I go to pick the first letter, I don't have 26 choices. I only have 1 choice because it has to be the letter R. So I only have 1 choice here. Now, when I go to the second letter, how many choices do I have? Be careful. I only have 25 now. Why? Because the first letter is R. I can't have repetition, so that R is now taken out of the 26, and now I have 25. So the second letter I have 25 choices. Once again, this number is going to start going down. And my pen will stop writing, right? 25, 24, 23, 22. Always multiplication, okay? Even if you don't see it here and it makes a little line. Still trying to get used to working on the screen here. All right, so I picked my letters. Once again, the last question is always, do I have order? Again, this is an ID. I do have order. So this product right here is the answer to the problem. If you do the math, show yourself that this is 303,600. So again, this was a special case because the first letter had to be R. I only have one choice here, right? But the second thing I had to realize is that, well, I've selected something. When I get to the second letter, there's only 25 choices. And so therefore, my number starts at 25, not 26. Got it? All right, let's move on to probability. Our first probability question. A fruit basket contains 4 bananas, 5 peaches, 3 oranges, and 3 apples. You pick one piece of fruit at random, and we want the probability of picking an orange. The fundamental definition of probability is the number of ways you can do it divided by the number of ways you can do anything. And if you can use that definition, then that's probably the easiest way. In other words, if you can count your way through probability, that's probably what you should be doing. So, I know how many ways I can pick an orange. 3. I know how many ways I can do anything. 5, 8, 11. So, the probability of picking an orange, 3 out of 11. What's the probability of not picking an apple? Well, the number of ways I can pick something other than an apple, 5 and 3, 8. How many ways can I pick something? 11. So 8 out of 11. The next one, what's the probability of picking an apple or a banana? Well, apple or banana. Oh, wait, I'm sorry. See, caught my mistake. There's 4, 9, 12, 15 things, right? So that is 3 over 15. That's messed up. Caught myself, but not edited. Okay, I didn't see the bananas over there. They're big yellow things, but I didn't see them, huh? All right, not picking apple, 4, 9, 12. There are 12 ways of not picking an apple. There are 15 ways of picking something, right? Good thing you caught yourself, though. Find the probability of picking an apple or banana. Well, 4 ways in banana, 3 ways in apple. So getting an apple or banana, 7 ways. 15 ways of doing something, right? 7 out of 15. Okay? Now, you should reduce fractions to lowest terms, right? I'm just saying that. I personally would rather just see this because it shows me where the numbers are coming from. But officially, the formal rule is fractions are in lowest terms. But I'm grading your paper, so you don't necessarily have to do that. All right. I'm getting near the 15-minute mark, so I'm probably going to do this one, and then I'm going to cut the video and start a new video. All right. Suppose we're given the following information. The probability of event A is 1/2, the probability of event B is 0.4, and the probability of A or B is 0.4. We want the probability of A and B. Notice I have the probability of A or B. There's a formula for that. The probability of A or B is the probability of A plus the probability of B minus the probability of A and B, right? Whenever you see A or B in a problem, you probably should be thinking that. Notice I didn't have to do that up here. Why? It was a simple counting problem. And if you can count your way through probability, that's probably the fastest way. Now back to this problem here. I know what the probability of A or B is, 0.4. I know the probability of A, 0.5. I know the probability of B, 0.4. I don't know the probability of A and B. That's what I want. But this is a linear equation. I can solve for x. X is 0.5 plus 0.4 minus 0.4, right? Bringing the 0.4 over across. So x is equal to 0.5. So the probability of A and B, 0.5. The probability of B given A, well, now this is a little tricky one, because you know the probability of A and B is the probability of A times the probability of B given A, right? Now the formula you're supposed to know. Well, you know what the probability of A and B is. It was done in part A. The probability of A is 0.5. So what's the probability of B given A? You bring this to the other side, and you get 1. The probability of B given A has occurred is 1. Alright, I'm going to end the video here.